Hi all, this video is going to take you through the marking schedule for the reactivity paper for 2019. So question 1a, nitrogen tetroxide is a colourless gas which decomposes in equilibrium to form the brown gas NO2. Write the equilibrium constant expression for the following reaction. So equilibrium constant is products minus reactants. Let's get it right, KC, products, reactants. So in this particular case, our products are NO2. And we write this in square brackets to represent the concentration of NO2, and the reactant is your N2O4. So products over reactants. The second thing you have to look out for is the number of moles of chemicals. So if it is a 2, it means we square it. If it's a 3, we cube it. If it's nothing, we just leave it. So because there's 2 moles of NO2, we put a little 2 up top, so we square it. At 25 degrees Celsius, Kc is 6.1 times 10 to the minus 3. Circular species that will be present in a greater concentration at 25 degrees. So times 10 to the minus 3 is a small number, and whenever Kc is smaller than 1, it favours reactants. Whenever it's larger than 1, it favours products. So Kc is less than 1, therefore it favours reactants. And the reactant in this particular case is N2O4. Explain using equilibrium principles the effect of increasing the volume. So when you increase the volume, you decrease the pressure. Okay, so whenever you change the volume of a system, it's always a pressure type question. So you decrease the pressure. Le Chatelier's principle, whenever you make a change to the system, it tries to minimize it. So try to minimize the change. So if we've decreased the pressure, it's going to try and minimize the change by increasing the pressure. Okay. The thing with this particular type of reaction is whether you have 1 mole of hydrogen, which is a really small molecule, or 1 mole of methane, which is slightly bigger, they both take up the same amount of space. That's the kind of theory behind this particular question. So if you look at our question, on the left-hand side, we have 1 mole of N2O4. On the right-hand side, we have 2 moles. Okay, so this side, because there's 2 moles, is going to take up twice the amount of space as the left-hand side. Okay, so to try and increase the pressure, we're going to favour the side with the most moles of gas. Which in this particular case is the products. So 2 moles versus 1. Therefore, forward reaction will be favoured. And more NO2. And in the particular question, you're told that N2O4 is colourless and NO2 is brown. So if we're producing more NO2, it's going to go darker brown. Alright, next one. Solution of dichromate, which is normally acidified, is contaminated with chromate. So basically you've got this equilibrium where you've got dichromate and hydroxide as the reactants, and chromate and water on the right, which are products. Dichromate you're told is orange, and chromate you're told is yellow. So they go through 2 changes and you have to explain what will happen. So if you add more hydroxide, what you're doing is you're adding more hydroxide, which is affecting the reactants. So this is a concentration question. So what you've done is you've increased the concentration of OH minus. According to Le Chatelier's principle, it doesn't like that you've done this, so it's going to try and minimize change. And the way it does this is it favors the forward reaction. And to get merit, this is what a lot of people missed off. The reason why it favours the forward reaction is to use up the excess OH minus. Okay, so it favours the forward reaction so that it can use up the excess OH minus. This in turn creates more of the chromate ion. And because the chromate ion is yellow, it becomes more yellow. Good way of doing it. Alright, number 2, dilute acid is added. Now, lots of people, for some reason, just assume that if you're adding acid, you're affecting the right-hand side of the equation. But nowhere on the right-hand side of the equation is there acid. So, if you were to add acid, what actually happens is the acid reacts with the OH minus to form water. So what you're effectively doing is removing hydroxide from the system. Okay, and according to Le Chatelier's principle, it doesn't like that you've made a change. It's going to try and replace all of that lost hydroxide. And the only way it can do that is by favouring the reverse reaction. To replace the lost OH minus. The other common thing that people said was it favours a reverse reaction to create more hydroxide to counter the hydrogen ions. And I didn't give that because it's not quite correct. So the hydrogen ions react with the hydroxide, so because you're losing hydroxide, the system's going to try and replace it. So when you favour the reverse reaction, you create more of the dichromate ion, therefore it is going to go more orange. Finally, we're on to part C. You're given a reaction, the decomposition of hydrogen sulfide, and they're nice enough to give you the Kc expression. So because it's 2 moles of H2S, it's squared. Because it's 2 moles of hydrogen, it's squared. So calculate the concentration of hydrogen gas present in equilibrium mixture when the concentration of the gases is such. So first thing you should always do is write down the Kc expression. Normally you have to work it out, but they were really, really nice and they gave it to you. Next thing you should do is plug in the numbers. What do you know, what don't you know? So you're told up here the value of Kc. So Kc is equal to 1.67 times 10 to the minus 7. Hydrogen, that's what we're trying to work out, the concentration of a hydrogen, so that's left blank. Concentration of sulfur, they tell you down here is 0.072. So times 720. And the concentration of H2S, you're told, is 0.160. Now, because it is squared, we need to square the number over here. And lots of you didn't do that, and that's why you didn't get any marks. The achieved mark was to substitute the numbers incorrectly, and because you put it into the wrong formula, you're not given that mark. So once you've got that, using your calculator, you can work out the concentration of hydrogen squared, 5.94, and then you just have to square root that. And you get 2.44 times 10 to the minus 4. So unit, because it's a concentration, is moles per litre. And we always round to 3 significant figures. Part 2, when the temperature increases, the Kc value increases. Justify whether the decomposition is exothermic or endothermic. So there's two kind of key ideas to this. Number one, if Kc increases, this tells you that the amount of products is increasing. So whenever Kc gets bigger, it means you've got more products. And because you're getting more products, it means the forward reaction is being favoured. So that's your kind of first key idea. Second key idea is that when you heat the system tries to minimise the change. So it tries to minimise the change by favouring the endothermic reaction. To cool it down or use up the excess heat. Okay, and then by combining those two bits of information, we know that the endothermic reaction is being favoured to try and cool it down to use up the heat, and we know that the forward reaction is being favoured because we know we've got more products, therefore the forward reaction is endothermic. On to question 2. You're doing a rates of reaction question where 4 different experiments took place between calcium carbonate and hydrochloric acid. And they change different factors between the experiments and you have to explain why. So rates of reaction, it's exactly the same as what you did in year 11. You don't have to do anything different. It's just remembering what are the different things you can do to change the rate of reaction and then referring that to the how that affects the particles and the frequency of collisions. So number 1, name the factor affecting the rate of reaction that's investigated in experiments 1 and 2. So looking at 1 and 2, volume of HCl is the same, volume of water is the same, the mass is the same, you've used powder versus chips, and temperature is the same. So the thing that has changed is powder or chips, and you need to recognise that that is measuring surface area. Okay, predict and explain the relative rate of reaction for experiment 1 and 2, refer to collision theory. So it's just your typical typical answer for surface area. So when you go from a powder to a chip, experiment 1 uses powdered calcium carbonate, and what that does is it increases surface area. Okay, when you increase the surface area, it means more calcium carbonate is exposed to the acid. When more calcium carbonate is exposed, that means you get more frequent collisions, more collisions per second. And if you have more frequent collisions, you get a faster rate of reaction. And that is it. That's as simple as the answer needs to be. There's basically 3 kind of ideas, and for any rates of reaction question you do these 3 ideas. Number 1, identify what has been changed. Number 2, relate that to the particles. Number 3, relate that to the frequency of collisions. And if you do that, you'll be absolutely fine. Okay, part 2, name the factor affecting the rate of reaction that has been investigated with experiments 2 and 3. So if you go back to your table, the thing that is different is the volume of HCl and the volume of water. Okay, so whenever you're changing the volume of the chemical, what you're doing is you're either diluting it or increasing the concentration. So because one of them has more water than the other, the factor we're doing is concentration. So what would be expected the rate of carbon dioxide gas, why experiment 3 is slower than number 2. So if you look at experiment 3, it's got 10 mils of acid and 10 mils of water, versus experiment 2, which is 20 mils of acid. So experiment 3 has a lower concentration of HCl. And lower concentration of HCl, what that means is you've got less hydrogen ions per unit volume. Okay, for those of you that don't know what that means, if you take an acid which is 1 mole per litre, take an acid which is 5 moles per litre, they're each going to have a certain amount of hydrogen. But if you take a little snapshot of the 1 mole per litre acid versus the same size snapshot of the other 5 mole per litre, you can see that there's a lot more hydrogen ions in that little snapshot. So that's what it means per unit volume. If you take a small amount of space, how many hydrogen ions are going to be in there? So less hydrogens per unit volume means less frequent collisions. Less frequent collisions means a slower rate of reaction. Okay, again, I've got my 3 key ideas. What have I changed? How does that affect the particles? How does that affect the collisions? Alright, jumping down the page, comparing experiment 4 and 3. So if you look at experiment 4 and 3, the difference is the temperature. So experiment 3 is done at 25 degrees, experiment 4 is done at 45 degrees. So the factor is temperature. Okay, and we're told that the rate of reaction is faster in experiment 4. So experiment 4 has higher temperature. Okay, when you change temperature, there's 2 kind of key ideas that you have to actually talk about. So number 1, because it is hotter, it means particles move faster. And if particles move faster, you get more frequent collisions. The second factor, because they're hotter, they've all got more kinetic energy. So I'll just use EK for short. And because particles have more kinetic energy, It means more particles have enough volume to collide successfully. Okay, don't talk about force, talk about energy. Have enough energy to collide successfully. Okay, so what that means is there's more collisions where the particles actually turn into products than collisions where they don't have enough energy and they just bounce off. Okay, because you've got more particles that have enough energy to collide successfully, you get more frequent, successful collisions or effective collisions. So I can learn how to spell. Now, because of those two factors, you get an increased rate of reaction. Right, lucky last. Question number 3. Complete the table by writing the formula of the missing acid or conjugate bases. So first of all, what the relationship between acid and conjugate base is they differ by a proton. So you learnt about the new definitions this year. Acids are things that donate protons, bases are things that accept protons. So if your first acid is HCN, the definition of an acid is it's a proton donor, so it's going to get rid of this proton somewhere, and when you get rid of that proton, you're left with a CN. Now we all know that protons are a positive charge, and when you lose a positive charge, that must mean you're left with a negative charge. Alright, conjugate base. Bases are proton acceptors. Okay, so you've got this chemical here, and that when it gets rid of an acid, it turns into your conjugate base. So the difference between the two things is a hydrogen ion. So in this particular case, this one here must be H2CO3 minus. Okay, because when this donates a proton, it's left with just one H. Now I've made a small mistake there. Because we're gaining a proton, we're gaining something with a positive charge, so it's actually going to have no charge, it's neutral overall. Last one, H2PO4 minus. It's an acid, it's a proton donor. That hydrogen's going to go somewhere else. You're left with HPO4. And because we've lost the positive charge, it started off with a -1 charge. -1 minus 1 is -2. So, explain the relationship. They differ by a proton. So, HCN donates a proton. To form Cn minus. So when it loses its hydrogen, it's left as Cn minus. Alright, part B, calculate the pH of a 0.022 mole per litre solution of nitric acid. So nitric acid is a strong acid. So when it dissociates in water, it fully dissociates into nitrate ions and hydronium ions. Okay, reason why that's important is the way we calculate pH is minus log H3O plus hydronium ion. Okay, and because it's a strong acid, if we have 0.022 mole per litre of nitric acid, we have 0.022 mole per litre of the hydronium ion. So all you do is minus log 0.022 and you get 1.66. Okay, the reason why we can't work out pHs of weak acids is because weak acids don't fully dissociate. So even if you're given the concentration of the acid, you don't actually know how much hydronium ion there is. Right, you have some pHs, so you need to work out what the concentration of the hydroxide is for these three particular chemicals. So there's a couple of ways you can work that out, and I'll go through both of them. So if we start off with solution A, the main way that you do it is it's a kind of two-step process. Because we know the pH, we can work out what the hydronium concentration is. So that is equal to 10 to the minus pH, which in this particular case is 10 to the minus 11.2 from here. And that gives you 6.31 times 10 to the minus 12. The second formula you're given is Kw. So Kw is equal to hydronium ion concentration times the hydroxide ion concentration. Kw is always 1 times 10 to the minus 14. Hydronium ion concentration you just worked out. And hydroxide is what we're trying to work out. Therefore, you work out hydroxide is equal to 1.58 times 10 to the minus 3. The other way you can do it, and I'll use B as an example, if the pH is 13.2, then the pOH is equal to 0.8. And from there you can just kind of use the opposite of this formula here, or the equivalent I should say. So the hydroxide ion concentration is equal to 10 to the minus pOH, is equal to 10 to the minus 0.8, which equals 0.158. And because we're talking about concentrations, it's mole per litre. I need to correct that for A. Alright. Finally, part C. The pH is based on the amount of hydroxide ion versus hydronium ion. So because A and C both have the same pH, they're going to have the same concentration of ions. So the hydroxide ion concentration for C is the same as A, which is 6.31 times 10 to the minus 12. Right, on to part 2, compare and contrast the relative strengths of the bases and justify the variation in pH values. So what we can see is B and C are both strong bases. And the reason why is the concentration of hydroxide ions in the solution is the same as the original concentration. And what that means is they fully ionize or dissociate. Okay, so because the two concentrations are the same, they fully ionize, therefore it is a strong base. A, on the other hand, is a weak base. And we can tell that because the concentration of hydroxide ions is less than the original solution. Okay, so it's only partially ionized. Okay, so only some of them actually produce hydroxide ions. Okay, so that gives us a couple of things to compare. So first of all, B and C are both strong, but B has a higher pH. And the reason why it has a higher pH is it has a higher concentration. So because it's got a higher concentration, it produces more hydroxide ions, therefore has a higher pH overall. The other comparison we can make is between A and C. So A and C both have the same pH, which means the same concentration of hydroxide ions, but different initial concentrations. Concentrations, which means they ionize differently. So because A has a higher original concentration, that must mean it doesn't dissociate as well as C. And that makes sense because A is a weak base. Right, on to part D. pH and relative conductivity of two solutions are given. You can see the ammonium chloride has a low pH of 5.11 but is a good conductor, whereas methanoic acid has a pH of 2.36 and is a poor conductor. So write equations to show reactions of these two in aqueous solutions. So you guys need to be able to recognise what chemicals are weak acids, weak bases, strong bases, and which ones are just salts. So whenever you see a COOH, you need to recognise that this is a weak acid. It's a carboxylic acid. And carboxylic acids, what they do in water is they partially dissociate. You end up with the methanoid ion and hydronium ions. Okay, so whenever something only partially dissociates, that's when we use the equilibrium arrow. Ammonium chloride is just a salt, and whenever you stick a salt into water, it completely ionizes, it breaks apart, in this case into the ammonium ions and chloride ions. Now, whenever you see the ammonium ion, something needs to trigger in your head that this is special, and the ammonium ion is actually a weak acid. Because it's a weak acid, it will react with water, and it will partially dissociate into NH3 plus hydronium ions. Okay, explain the difference in pH of these two solutions, refer to your equations. So, what you can see is that methanoic acid has a lower pH, and because it's got a lower pH, that means it has more of the hydronium ion. And the reason why it has a lower pH is because it must be a stronger acid. So therefore, Must be slightly stronger. Or dissociate more. Than NH4+. Okay, so because it dissociates more, produces more hydronium ions, which gives it a lower pH. Alright, part 3, explain why ammonium chloride solution is a better electrical conductor than methanoic acid. So these types of questions are always in the exam, and the thing that determines electrical conductivity is the concentration of ions. So you need to work out which one has a higher concentration of ions. So ammonium chloride is a salt, which means it fully dissociates, or fully ionizes, splits apart into ions, into NH4+. Therefore, it's got a high concentration of ions, and therefore it's a good conductor. Methanoic acid, on the other hand, is a weak acid, so only partially dissociates. Therefore, there's a low concentration of ions. Because there's a low concentration of ions, it is going to be a poor conductor. So, hopefully that video helps answer any of your questions. If you've still got more or you're confused by things, please ask either myself or Dr. Taylor. Cheers.